Okay, 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 okay. Hello. Hello, 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 hello. हेलो हेलो, लेट्स स्टार्ट करो। हाँ, ठीक है।
ये बोलते हैं ना कि लेट्स वेट।
So, hello everyone. Let's wait for a few more minutes. Hope some more students will be joining. Then we can start. सुनाई दे रहा हूँ ना?
तुम्हारा तो मुझे कोई नहीं बोला।
हाँ, ठीक है। नहीं नहीं, मेरा सुनाई दिया ना? Okay, let's start. I hope I am audible, right? Am I audible? Okay, thank you. So, hello, hi everyone. I am Orko Chakraborty. First of all, I would like to say Happy Republic Day to all. I am Orko Chakraborty. I am a PhD student at IIT Kanpur. I am doing my PhD in Electrical Engineering, Microelectronics, and VLSI. My research topic is neuromorphic computing and its allied domains. So I'll be conducting weekly doubt clearing sessions. These are kind of doubt clearing sessions where I'll be taking previous year's assignments and I'll be solving it for you. Also, as it's a 2 hour session and I must complete 2 hours, it is a requirement for my TA duty. So, and if I know that hopefully it will be over within 1 hour or 1.5 hours, so I will be taking some important topics, or I will be presenting some additional questions from my side, or I will be taking some internal topics and I will discuss on it, which I believe has not been included in the syllabus, but as a student, when I was doing the course, I found them to be important. So basically today we'll be looking into the week 0 and week 1 questions of previous year. I will be solving it for you. I will be trying to be elaborate as much as possible. Still, if you have any confusions, you can simply raise your hand or you can type the question, or I will be sharing my mail ID at last. You can simply give me a mail. I will try to get back to you within as quickly as possible. So let's start. Okay, so people are still coming. Okay. So first of all, we have a question regarding a basic RC circuit, which you must have, which you must be very familiar with since your school days, class 12 days. So basically, what it is told that in an RC circuit, which one of the following profile best describes the charging current? The options are exponentially increasing profile with respect to time, square of exponentially increasing profile with respect to time. So first one is saying something like e to the power t. Second one is saying square of exponentially increasing profile with respect to time. So e to the power 2t. Next one is saying exponentially decreasing profile with respect to time. So e to the power minus t. Square of exponentially decreasing profile e to the power minus 2t. Linearly decreasing profile, that is simply minus t. Linearly increasing profile with respect to time, constant profile, that is some constant k, or triangular profile, some kind of like such kind of profile it is being described. So basically we must know, everyone knows it is an exponentially decreasing profile, but let's look deep how this exponentially decreasing with time is coming. So So basically, let me consider a simple RC circuit. So let me write it as R. It is the C. Say there is a source here. The source is called Vs, and the input is such kind of a wave where it is 0 at, and this is the instant at t equal to 0. It is switching to say voltage VDD. Okay, so let me call this voltage as Vc, this voltage across the capacitor, and the voltage across the resistor let me call as Vr. Okay, so we know simple Vs is equal to here Vr plus Vc. Okay, and if current I is flowing through here, then this would be equal to I into R plus Vc. I is the current flowing through this circuit. Okay, So uh, we know the current through a capacitor, the I can be written as I equal to C dV dt, where V is the voltage across the capacitor. In our case, it is C dVc dt. Okay. So my Vs would be equal to C dVc dt into R plus Vc. Fine. Okay. Now let me rearrange it. So if I rearrange the equation, it would become dVc dt equal to Vs minus Vc divided by Rc. Okay. And say initially the capacitor was not charged, so my initial condition, the initial charge was 0, so initial voltage was 0 volt, no initial condition. So when I integrate it, let me write it in this form: dVc by Vs minus Vc equal to dt by Rc. Okay. So I'll be integrating it. The voltage initially was 0, and finally let me call it another volt. Let me name it Vc only for simplicity. The final voltage is Vc at time from it started from 0 at time t. Okay. So after integration, you can see here I will get what I will get. I will get negative log. I will get minus ln Vs minus Vc. Lower limit is 0, upper limit is Vc. Okay. And here I will get T by Rc from 0 to T. Okay. So it would become ln Vs minus Vc minus ln Vs equal to minus T by Rc, something of this sort. This is minus here. Okay. So now I can write it as ln Vs minus Vc by Vs equal to minus T by Rc. So from here I can divide it. So 1 minus Vc by Vs will be equal to exponential of minus T by Rc, which is equals to from here I can write Vc equals to Vs 1 minus e to the power minus T by Rc. Okay. This is the equation. Let me write it here clearly. So Vc would be equals to Vs 1 minus exponential of minus T by Rc. So this is the voltage equation for an RC circuit. Okay. So you can see at t equal to 0, my Vc would be 0 because it will be 1 minus 1, 0, and at t equals to infinity, it would be Vs 1 minus e to the power minus infinity, that is 0, so it would be equal to Vs. But generally we know we don't need to wait for infinite time period. After 2 to 3 cycles, after 2 to 3 RC, generally we get the voltage equals to the Vc almost becomes equals to the VDD. So now how to find the current? We have seen from the above that I was equals to C dV dt, right? So I equals to C dVc dt. So let me derive C dt of Vs 1 minus exponential of minus T by Rc. So it will become if I do derivative, this will cancel out, it will become this will come, minus will come, minus e to the power minus T by Rc. So minus minus cancel and Vs will be there. So it will become Vs by R. Can you guys kindly mute yourself? Minus T by Rc. Someone has unmuted themselves. Can you kindly mute yourself? Okay, thank you. Now, who is this? Akshay, right? So, Akshay, can you kindly mute yourself? Noise is coming. Akshay, thank you. Okay, so you can see the current is exponentially decreasing with time. So the correct answer would be exponentially decreasing profile with respect to time. Okay, but generally everyone knows this because we have been doing it since long. We all are electronics engineers or electrical engineers, so it's pretty obvious. But I wanted to show you how it is coming. So let's go to the next question. The question is, how many 2-input XOR gates are required to represent some expression of 1-bit full adder? Okay, fine. Everyone knows the expression that for sum the expression is. Am I missing some question? Yes, I am missing one question. Sorry. Okay, so the next question is, how many 2:1 multiplexers are required to design a 16:1 multiplexer? Fine. So there is a shortcut way and there is an detailed way. Let me first tell you the shortcut way. It's simple. See, if I want to design a 16:1 mux using 2:1 mux, I need to do it in multiple stages. So there will be multiple stages of 2:1 mux. So how many number of multiplexers will be required in the first stage? It's simple. As it is a 2:1 mux and there are 16 inputs, so I will require at least 16 by 2, that is 8 muxes. Okay, in the first stage. Second stage, there will be 8 inputs and I'll be using 2:1 muxes, so there will be 8 by 2, that is 4 muxes in the second stage. Similarly, in the third stage, there will be 4 inputs, so 2 muxes. And in the final stage, it will be 2 inputs, so 1 muxes. So total will come to be 15. So 15 2:1 muxes are required to design a 16:1 multiplexer. Now a little detailed, I want to show you the analysis. Say it is my 16:1 mux. Dot dot dot. So inputs are I0, I1 up to I15. This is my output. There will be 4 select bits S0 to S3. Now how to arrange this select lines when you are using a smaller multiplexers to design a larger one? It's pretty obvious, but let me show it to you for analysis. Okay. So say in the first stage I have 8 such 2:1 muxes. I0, I1, I2, I3 dot dot dot, I14, I15. There will be 8 outputs. This is my first stage, right? This is the first stage. In the second stage, there will be 4 muxes, right? Because I have 8 inputs. So these 4 muxes will come here. Okay. Okay. So they will come in such a fashion. So okay. So now this outputs would again be fed to the next stage, which will contain 2 muxes. You can see something like this will be coming, and finally the final stage, the fourth stage. It is my final output. Now how to arrange the select lines? If you look into the truth table, or you can directly from intuitively also you can say how we will be arranging the select lines. Okay, so first stages will get S0 select line. Okay, all the multiplexers will get S0 select line. Second stages will get S1 select line. third stages will get S2 select line, and the fourth stage will get S3 select line. Now how it will work? Say I want to pass the first one I0. Okay, sorry, what happened? Say I want to pass I0. So what I need to send the input signal, the control signal, it should be 0 0 0 0. Okay, S0, S1, S2, S3. So you can see when 0 is selected, I0 will pass, I2 will pass, I14 will pass in this way. Okay, when S1 will get 0, it will again pass this 0. From here it will say it will pass I4 or something like that. Here it will pass I14. Okay, again when S2 will be 0, again it will pass I0, and when S3 is 0, again it will pass I0. So finally I will be getting the output as I0. Okay, the I0 will be selected. Similarly, if I want to pass I15, I have to give the control signal as 1111, and let me use different color. Okay, and when S0 will get 1, it will pass it will pass I15, it will again pass I15, it will pass I15. Similarly, it will pass I15. I will get the output as I15. Similarly, you can figure it out that for any given condition, my particular input will be selected and will be passed to the output. And the number of multiplexers required, as I already mentioned, simply you can use this technique to find the total number of multiplexers required, which will be 15. Okay. Okay. So let us move to the next part. Next question. So the next question is, how many 2 input XOR gates are required to represent the sum expression of 1 bit full adder? So we all know the expression of an 1 bit full adder. For sum it is A XOR B XOR C in, and for C out it is AB plus BC in plus C in A. So for sum I need, you can see, 2 XOR gates. Okay, I hope here everyone knows the expression of a full bit or 1 bit full adder, or let me just quickly derive that for you. Okay, so say I am having say I am having a half adder here. So the 3 inputs are A, B, and the carry in, and the 2 outputs are sum S and the carry out C out. So the truth table would be fine. So it will be 0 0, it will be 1 0, it will be 1 0, it will be 0 1, and it will be 1 0, it will be 0 1, it will be 0 1, it will be 1 1. Okay, fine. Now let me draw the truth table for S. C in 0 0 0 0 0 1 1 1 1 0. Why 1 1 1 0? Because of gray coding, right? Okay, so S for S it will be 0 0 0 0 is 0, 0 0 1 is 1, 0 1 0 is 1, so 0 1 0 is 1, and 0 1 1 is 0, and 1 0 0 is 1, and 1 1 0 is 1 0 1 is again 0, 1 1 0 is 0, and 1 1 1 is 1. So you can see there are no common terms here. so you cannot simplify it further. So my S should be, expression would be, say this one, S expression would be, let me write it in red, a b bar c in bar, this one, then plus a b bar c in this, plus a b c in this one, and plus a b c in bar. Okay, so if I take c in bar as common, so I'll get a b bar plus a bar b. This I'm cutting this one. And where is c in this one, c in bar b, a b bar c in bar. Okay, so it will be a b c in bar. Okay, fine. So plus c in it, I will be getting something at around, it should be something like this. Okay, so basically I'll be getting c in bar a XOR b plus c in a XNOR b. Why XNOR? Because XNOR is the complement of XOR bar. So it is again in the form of a b bar plus b bar a. So finally I will be getting as a XOR b XOR c in. Okay, so here this is the expression of sum. So this is what I have written here, and so we'll be getting 2 XOR bits. So answer is 2. For a compact so let's move to the next question. Okay, someone is asking some question. You have written expression for 3 bits, but they asked for 1 bit. Okay. See, it is an 1 bit, sorry, not half adder, it will be full adder, right? It will be full adder. So the question is, I required to represent some expression of 1 bit full adder. One bit full adder. I think this is 1 bit full adder, right? Because you will have see, when you are making an n bit full adder, okay, you are making an n bit full adder. Say it is a 4 bit full adder, okay. So it will be something like this: A0, B0, A1, B1, A2, B2, A3, B3. Okay, so it would be S0, S1, S2, S3, C out. So its C out will go to C in of this second one, this C out will go to C in of second one, this C out will go to C in of the last one. So here the output bits we are counting, okay. The output bits we are counting. Here the output bits are 4 bits. So it is a 4 bit full adder circuit. It's a simple 4 bit full adder circuit, okay. And if I consider only this part, as you can see, there is only one output. As there is only one output, so S0, so this is a 1 bit, this is a 1 bit full adder, okay. If I am using multiple such full adder blocks, we'll be getting multiple bit full adder. And someone is asking something, what it is, ABCs are 3 bit, right? Okay, ABCs are 3 bit, but here when I am saying an 1 bit full adder, I am meaning that the output bit S is 1 bit. If it was 2 bit full adder, then the output bit S would have been of 2 bits, and so on, okay. And if I only considered A and B and not C in, it would be a half adder, okay. When C in is also considered, it is called a full adder circuit, okay. I hope it's clear. So the answer is 2 aggregates will be required, okay. For a compact design, how many flip-flops are required to define 11 states in a digital design? Okay. So how many flip-flops are required to define 11 states in a digital design? So basically, can anyone say me a single flip-flop can uh, can be used to represent how many stages? Anyone? Someone wants to check. Yes, two. So basically, one high, one low. Okay. So if a single flip-flop can be used to design represent two states, so two flip-flops can be used to design four states. So similarly, if I want to design a digital design where say n number of states are required, n number of states are required, then the number of flip-flops required would be basically log base to n. Simple. So here it will be log base to 11. But as you know, we cannot use a flip-flops in fraction, right? We have to use for whole flip-flops, 1, 2, 3 or 4. We cannot use 3.5 flip-flops. So here it will be the nearest number as 3, 8 gives me 8 states. For representing 8 states, I need 3 flip-flops. So at least to represent 11 states, I have to consider 16. I have to consider the case of 16 states. So it will be log base to 16. So okay, so 4, right? So if I was saying that I need 16 states, I will be using 4 flip-flops. If I need 9 states, still I have to use 4 flip-flops, right? Because I cannot use a flip-flop in fraction. If I need 17 states, then I have to use 5 flip-flops, which will give me 32 possible states to be used. Someone is asking, D flip-flop have 1 state, right? See, digital flip-flops, like D flip-flops you are talking about, still what it is storing, either a high or a low, right? So basically it is storing 2 states. So flip-flop is a memory device, okay? So we use memory devices to store at least 2 states. Multiple states can be, single device can be used to store multiple states also. Some new emerging memories are coming, such as flash memories that you use in SSD, or say ferroelectric FETs, which have been known to show multi-level capabilities. But basically, any memory device that you are using should be able to store at least 2 states, so that it can be used to store at least 1 bit. Okay, 1 bit means 2 states. So I hope that answers your question. Okay, fine. Okay, so let's move to the next part. The next question is, in a combinational circuit with multiple inputs and output, identify one of the statement which is correct. Okay, fine. Have I finished week 0? No, week 0 is still not. Okay. Okay. See, here it is talking about propagation delay and contamination delay. So the propagation delay for a combinational circuit and sequential circuit, their origins are different. Okay, but let me give you a quick mnemonic to remember them. Always remember that contamination delays are the best case delays. Okay, by best case delay I want to say, I mean that contamination delay will come for the minimum time condition. These are the best case delays, and propagation delays are the worst case delays. Okay, so now let's move and see what is given in the question. The minimum delay for different input combinations generating output is considered as propagation delay. So I said that for propagation is the worst case, means it takes the maximum amount of time. So minimum is, it is false. Okay, Second one is the maximum delay for different input combinations generating output is considered as propagation delay. Okay, so maximum means worst case, so it is true. Propagation delay is the worst case delay. Third one is the maximum delay for different input combinations generating output is considered as contamination delay. As I already said, contamination delay is for best case, that is minimum case, so it is also false. Fourth one is the contamination delay is defined for the input combination which generates lowest power. No, contamination delay and propagation delay doesn't have much to do with power. So this statement also doesn't make any sense. Fifth point is the contaminated delay is not applicable in combinational circuit. No, it is applicable both in combinational circuit and sequential circuits, though their origins are different. But contamination delay and propagation delays are present in both. And you might have heard about some terms like these are called what it is called setup time and hold time. Okay, so contamination delay and propagation delay are the defining factors in this setup and hold time. How they are coming, how they are generating, we'll be seeing in the subsequent lectures. We'll be seeing that. But for now, just remember this mnemonic, this short thing, and this kind of questions you can easily solve. So next is linear combination of contamination delay gives propagation delay. No, no. So there are some other factors also, some things you have to consider. So this is also false. Next is propagation delay for different combinational circuit remains same. No, not a chance. It will of course depend on the circuit, the transistors that you are using or the circuitry that you are using, and it will vary from circuit to circuit. Finally, is contamination delay for different combinational circuit remains same. It's also false. It doesn't make any sense. It will vary from circuit to circuit. So the only correct option is option number 2. Okay, let us move on. Okay, now we have completed week 0. Let's move on to week 1. Select true or false for the following statements. Okay, so the statement is n-type doping creates free electrons, p-type doping creates free electrons, boron is a p-type dopant. So it's basic of semiconductor devices, nothing else. Silicon has 4 valence electrons, right? Okay, so any atom which has more than 4 valence electron will act as an n-type dopant, like phosphorus, arsenic, antimony. So if I see the lattice of a silicon, it is basically bonded with other silicons. Still, okay. It is bonded with other nearby silicons. In such a manner. Okay. Now, when I introduce an n-type dopant such as phosphorus, what it will do? It is generally a pentavalent or hexavalent. Like it will either have a 5, 6 or higher number of electrons. Generally 5 or 6. So phosphorus has 5 electrons, right? So it will bond with nearby silicon atoms. Okay, but it will have an extra electron with itself. Now this is a free electron. Okay, it is relatively free electron because it is electron of the most outermost layers. So shielding effects and other will come into picture, and this electron is very loosely bounded with it. If we apply a potential, or even if you don't apply a potential at room temperature also, this electron will keep on moving between different lattice points. It will once go there, making this silicon negative and this phosphorus side positive. Then it will say move to the nearby this silicon atom, and this will randomly keep moving. If you apply a particular voltage, then say if you have applied a positive voltage in this way, so electron will get attracted towards the positive voltage, and this electron, it will still do jumping motion and it will move towards the positive voltage. Okay, now what in case of an trivalent atom? what if a trivalent atom like boron is introduced in the lattice? Let's see what happens. So if I introduce a boron, let me make it a boron. If I introduce a boron here, so boron basically has 3 electrons in its valence shell. So what it will do, sometimes when the temperature is high or an voltage is applied, some of the neighboring silicon atoms, electron will break from it and will come to the boron, making the boron negative, giving the boron negative charge. And here, as the electron has left it, so a hole will be present, like absence of electron will be generated here. Then this hole will again be filled up by another neighboring silicon atom. Say now this bond has been broken and this electron has come here, nullifying this bond, again generating this bond, but the hole will move here. So this absence of electron is acting like another particle, we call it a hole, and it will start moving. Now if I apply a positive voltage here, negative, so it will move away from the positive voltage due to this electric field. It will again do this jumping kind of motion and it will start flowing away from the positive volt. Now you will notice one thing, that phosphorus, that the electron was loosely bound, okay, it was more of a free electron. But here, as bounded electrons are involved, I have to break the bond for the hole to move. So the bond needs to be broken for the hole to move. More amount of energy is required for breaking such kind of bonds. So more amount of energy is required for movement of holes compared to electrons. And that is one of the significant reasons, one of the dominating factors, that the mobility of hole is less than the mobility of electrons. If you have seen the lectures on the transistor, you would have noticed that mu p is generally less than mu n, and it is almost mu n is generally twice of mu p. Why? Because electrons are relatively free, whereas holes require breaking of electrons. That extra breaking energy reduces the overall mobility. Okay, so you remember this point, it will be used later on. So the statements were, n-type doping creates free electrons. True. N-type dopants have extra electrons in their valence, so they create free electrons. So first one is true. It is true. P-type doping creates free electrons? No, they create free holes. Okay. Boron is a p-type dopant? Yes, boron is a p-type dopant, as I have already mentioned here. So it is also true. So it is true, false, true. So what is true, false, true? Here it is. True, false, true. Okay. Now let's move to the next question. Okay, it is talking about an NMOS transistor. I would like to give you an basic introduction about how a MOS capacitor works, but let's go through the questions, and then I'll be giving you a quick overview of what is happening in an MOS capacitor, what is happening, so we'll understand what is this accumulation, depletion, and inversion. And I hope sir has already covered that in the class. Okay, so okay, so what happens? I'm having an NMOS transistor. Okay, metal oxide semiconductor, and it is an NMOS transistor, so the body would be p-type. Drain, gate, source. Okay, so when VGS is less than 0, that is, I am applying a negative voltage here, positive holes will be accumulated here. Okay, when VGS is less than 0, that is this condition, positive holes will be accumulated here. Okay, so this would lead to accumulation, that is this one. So 1 will so 2 will result in 1. When VGS is positive but it is less than VT, V threshold voltage, what will happen? When it is positive but less than VT, Basically what happens, two things happens before even inversion. There is something called as a weak inversion, okay, but let's not go into it. So what it will do, it will repel the holes, all the holes present, it will repel it, and slowly some electrons will start gathering here. Where the electrons will come from, you will ask that is a p-type semiconductor, where the electrons are coming from. These are the thermally generated electrons, the thermally, because we all know that electron hole pair generation is continuously happening inside a semiconductor, right, due to thermal excitation. So these thermally generated electrons will slowly start coming here, and the holes will start uh, moving away. As the holes, the carriers are moving away, the free carriers holes are depleting. So it will lead to, this condition will lead to depletion. Okay, so one will lead to depletion of majority carrier set, that is the p type. Now when VGS is greater than VT, the holes have moved away, and the electrons have accumulated here at such number that it has made this region basically n type. Okay, so this is called an inversion. There are two kinds of inversion, basically weak inversion and strong inversion. And where the this boundary of weak inversion and strong inversion lies, it is something as psi s equals to 2i phi f plus something. And there are some, a number of literatures are available. What is the actual definition of VT? And the actual definition of VT is really tricky. Generally what industry people do when they make the compact models or they are doing any measurements, what they do, they use something called as a constant current method. They start increasing the gate voltage, and at the point where they achieve a particular target current, they say yes, we have achieved VT. Because if you go to the analytical models where physics is involved, like so many definitions are available, because phi f is involved, body effect coefficient gamma comes into picture. So industry people generally prefers the constant current model. Okay, but VGS is greater than VT. Could you repeat depletion and inversion conditions, sir? Okay, okay. Let me do one thing. At the end I will be talking about 2-terminal MOS and 3-terminal MOS. Okay, on that time I will be talking about it in more detail. So just be with us for a few more moments. Okay, then I will be talking about that part, because I will be anyhow repeating that part. Okay, hope it's okay with you. Who said it? Netra. Hi Netra, I hope it's okay with you. Just wait for a few more minutes. I'll be talking about that in 2-terminal MOS model, MOSFET model. So 3 will be inversion, right? So 3 will be 2. 1 will be depletion. So 1 will be depletion, 2. 3 is inversion. Inversion is 2. 3. Okay. So okay. So 1 is 3, 2 is 1, 1 is 1 is 2, 1 is 2, 1 is 2, 1 is 2, 2 is 3, 2 is 3, this one. So this one is the correct answer. Okay, 3 is 1. Okay, let's move to the next one. It is given for an NMOS transistor. W is given, L is given, width is given, length is given, thickness of oxide is given, mobility of the NMOS is given, permittivity is given, epsilon oxide, gate voltage is given, drain voltage is given, source and body voltage is given, threshold voltage is given. Basically it's a 65 nanometer technology node. Okay, they have asked us to find the current IDS. Now they have asked us to find okay, simple IDS. Okay, it's simple. Now I would like to be specific here. The most mistake students do, even I used to do, while doing such calculation, arises from using of proper units. Okay, if you are using centimeter, stick to centimeter. If you are using meter, stick to meter, because it is the most critical source of error which can throw you by orders of magnitude from the result. Okay, so always keep in mind to keep a track of the unit you are using. Okay, so IDS is basically, we know, mu1 Cox W by L VGS minus VT into VDS minus VDS square by 2. So, okay, so mu1 is given 80 centimeter square per volt second. Cox is epsilon ox by Tox. Is Cox given here? No, epsilon ox by Tox. So epsilon ox is 3.9 into epsilon naught, that is 8.854 10 to the power minus 14. Tox is Tox. How much is Tox? Tox is 1.05 nanometer. I will be writing it in centimeter. Okay, I will be writing it in centimeter. So 10 to the power minus 7 centimeter. W and L both are in nanometer, so nanometer will cancel each out. So it is basically 260 by 65. Vg is 1 volt, S is 0, so VGS is 1 volt, and VT is sorry. So let me write it here. So VGS is 1 volt, VT is 0.3 volt, and VDS is simply VD minus VS, that is 1 volt minus 0 volt, that is 1 volt. So and it is VDS square by 2. Okay, fine. You do it calculation. I have done the calculation yesterday night, and the answer I was getting is 257.8 microampere. Okay, here the answer is not matching with anyone. Here they have got 128.87 microampere, because I think just give me a minute. Number 3. See, it is asked here to find the drain saturation current, right? So the formula that I am using will not be correct. It will be, it will not be correct, because at saturation we know VGS minus, when VDS exceeds VGS minus VT, the formula that I will be using, I will be replacing this VDS with VGS minus VT. So it will become x square minus x square by 2. So it will basically become VGS minus VT whole square divided by 2. Okay, so here you will get into 1 volt minus 0 volt minus 0.3 volt, so it will be 1 minus 0.3 whole square divided by 2. Fine. So do it, you will get the answer as 257.8 microampere. Okay, now they have got the answer 128.87 microampere, but I am getting the answer as 257.8 microampere. I hope I am correct, and but you can cross check it. It might be some mistake from their part. The order you can check is correct, but what I am getting, the answer is double of what they are getting. Okay, maybe they have taken this 2 inside the square and they have mistakenly calculated it wrong. It might happen. Human errors are common among us, especially in device field. Okay, which condition? See, let me not go into let me have I written Cox? Yes, Cox is basically A epsilon ox by Tox, the parallel plate capacitor model that you have studied in class 12. Okay, here we are talking about Cox prime basically, which is Cox by A, that is epsilon ox by Tox. Okay, someone writes it as Cox prime, someone likes to write it as Cox only. So here capacitance is equals to epsilon of the oxide by thickness of the oxide, and as epsilon of the oxide is given here, it is epsilon r, that is 3.9 for basically for silicon oxide, and it is the epsilon naught, and Tox is given here 1.05 nanometer. So we will be getting the Cox as this value. Okay, and someone else is asking something. Please tell which formula how we have to use at which conditions, sir. Sure, I will tell you. Okay, so let me not consider the velocity saturation condition, simple saturation condition when pinch off has happened. See, this is my VDS, okay, and this is my IDS. Okay, so IDS versus VDS curve, we get something like this. Okay. Now here what happens, here the VGS is taken to be more than VT. This condition it is satisfied, and initially this is called the triode region or linear region of a transistor. Okay, triode or linear region. Okay, and this is called the saturation region. Why it happens? When I will talk about that 3T MOS, then I will move to 4T. I will give a brief introduction. I will be talking about that. Okay, that why this is how this is happening. And basically in saturation, if you keep on increasing VDS, your IDS will not increase. This is for long channel MOSFETs where say L is around 180 nanometer. Okay, but if you come to lower technologies, say 65 nanometer, 45 nanometer, or even lower 22 nanometer, 3 nanometer, say now Apple is using 3 nanometer from TSMC. There what happens, though VDS increases even in saturation region, the current keeps on increasing. This is due to channel length modulation, CLM. So along with this equation, you have to add one more term, lambda VDS. Okay, lambda is called the CLM coefficient, channel length modulation coefficient. Okay, let not go to such detail. For simplicity, let me tell you which model to use when. So in this region, the equation of the current is IDS equals to mu n Cox W by L VGS minus VT into VDS, okay, minus VDS square by 2. This is valid up to this point. This is called the pinch off point. Okay, up to this point for this equation condition, this equation is valid. And beyond this equation, you have to modify it. For this region, simply what happens, it gets pinched to, or it gets saturated to the value for this is for VDS, sorry, this is for VDS less than VGS minus VT. For VDS greater than VGS minus VT, what IDS becomes is simply mu n Cox W by L. I will be substituting the VDS by VGS minus VT. VGS minus VT square, because VDS has become VGS minus VT, minus VGS minus VT square by 2. So it becomes mu n Cox W by L VGS minus VT whole square divided by 2. Okay. Okay. Fine. In the above equation, how do you identify that formula will satisfy it, sir? In the above question, how do you identify that formula will be satisfied, sir? See, here it is mentioned for drain saturation current, right? It is mentioned here saturation current. So this region is called the saturation region. This region is called the saturation region. So for saturation region, this equation will be valid. As I said, VDS greater than VGS minus VT, it is called the saturation region, and this equation will be valid. That's why I use this equation. Okay, so by this we'll be getting it. Now if CLM was present, one lambda VDS term would have been added, but that's none of our concern right now. The question calculate current is given, so which current we have to find? In the question and calculate current is given, so which current we have to find? We have to find the saturation current, this current IDS. To find this IDS current. Okay. Check it, you will be getting something like this, and take the value of Cox as epsilon ox by Tox, and you should get this value. Okay. Hope it's clear to you. Next question is, select the true false for the statements. Okay, fine. Saturation current is more than linear current for MOS transistor. As I have already discussed here, you can see saturation current is always more than the linear current. The triode region or the linear current the saturation current is more than this. It's more than the linear region. Okay. So first condition is true. Sorry. First condition is true. As the gate source voltage increases for the same drain source voltage, drain current decreases. It is saying my gate source voltage is increasing while drain source is kept constant. So will drain current decrease? You can see even both the condition, it is my current is proportional to VGS minus VT square. You can see in both the conditions. Okay. Sorry, in linear region it is linearly proportional. In saturation region it is proportional to its square to the power 2. So the statement that it will decrease is wrong because it will increase. So this one is false. Okay. And if you see the one more thing, if you see the IDS versus VGS plot, it is something like this. Okay, here it is VT. When it cross VT, it starts increasing exponentially. Before VT also it is it increases, but it's more of linear. So if you look into the plot, the current is the plot is like this, exponentially increasing, kind of diode plot that you get. Okay, fine. So the third statement is NMOS transistor has less mobility, hence the saturation current is less compared to a PMOS transistor with the same physical parameter and gate source voltage. Now if you remember, I talked about it in the lattice here, that NMOS transistors, like, it is involving what? Electrons has higher mobility because they are free carriers, relatively free, whereas holes require breaking of bonds, so more energy is required. So the mobility of hole is less than mobility of electron. So this statement is also false. Okay. So this statement is also false. Now one more thing, if you look into the circuit design part, you will be designing lots of circuits in the coming lectures. So we will be seeing here for any CMOS circuit, complementary MOS circuit, what we do, say I am inverting an inverter here. Okay, I am designing an inverter here, not inventing, sorry. I am designing an inverter here. It's a CMOS inverter. Okay, here the W value for PMOS I'll be keeping as twice as W value of NMOS. If it is 1x, it will be 2x. Why? Because I want the same current, because NMOS is used for discharging and PMOS is used for charging the load capacitance here. Okay, so I want the current to be same so that the charging and discharging time is almost same. So as the mobility of hole is half the mobility of electrons, I have to compensate it somewhere in this equation. I have to compensate somewhere in this equation so that I get the same current. So as mu n is twice of mu p, so mu Wp is taken twice of Wn, so that it cancels out and I get the same IDS, charging and discharging current. Okay. So it is something that we will be seeing in your future lectures. So it is true, false, false. Where is true, false, false? Here is true, false, false. First one. Okay. Okay, now we have to do something. Okay. See, here it is asked that compute the effective mobilities, mu effective for PMOS and NMOS when the transistors are on. VGS is given 1 volt, VT is given 0.3 volt, TOX is given 1.05 nanometer for the 6 nanometer technology node. So in the lecture, if you have followed it, sir has given you the formulas that mu effective for PMOS is 185 centimeter square per volt second divided by 1 plus VGS plus 1.5 VT mod divided by 0.338 TOX volt per nanometer. Okay, so if you plug in all the values, you will get 1 plus VGS is 1 plus 1.5 into 0.3 mod 0.338. TOX is given as 1.05 nanometer, and nanometer will cancel, so I'll simply get 1.5 nanometer. Okay, so if you solve it, you will get the result as 125 divided by 1 plus 4.08, which is equals to 36.41 centimeter square per volt. See 36.4 here it is given 36.37. So this is the answer. But let me also do the mu effective for NMOS also. For NMOS, the formula is 540 centimeter square per volt second, 1 plus VGS plus VT inside mod divided by 0.54 TOX volt per nanometer. Okay, and here it is raised to the power 1.85. Okay, so if I plug in the values, it will come as around 540 plus 1 by 1 plus 0.3 divided by 0.54 into 1.05 to the power 1.85. Use your scientific calculators. You will be getting the value as 540 divided by 1 plus 4.641, 95.72 centimeter square volt. Okay, centimeter square per volt. See, 95.7, I am getting 95.72. So this is the answer. Now I would like to concentrate on a point. These effective mobilities equations that you are getting, these are not absolute equations. Okay, these are empirical equations. Now what are empirical equations? See what industry people do. If industry people sits on solving equations for designing circuits, like they are designing a circuit. See, they are designing a circuit in industry guide. They cannot simply go and solve analytical equations for that, right? So what they need to do, they come up with a clever idea. What they do, they use compact models. Okay, in compact models, what it is done, they use empirical equations. They fabricate the device and they make a model which is not completely based on the physics, but which is based on few parameters. Okay, and they tune the parameters to get the equation exactly as the experimental value, that is the fabricated value. Okay, so these values that it is coming here, 1.85 you can see here, 1.85 you can see here, or the equations that sir has written, that 185 centimeter square per volt second, these are not hard and fast values. Okay, this is only valued for 65 nanometer technology node. If I change the technology node, if I maybe use a different value of substrate or some, if I change the material, then it will change. Okay, it is completely different. For 3 nanometer it is different, for 5 nanometer it is different. So as it is mentioned here, you can study it, but we engineer guys generally don't bother about these equations. Like these are important for compact model point of view, but like there is nothing to memorize about it, because it will anyhow change in the next technology. Ideas are more important than the formulas, I believe. But for reference, you can use these formulas to find the effective mobilities. But you can use these formulas to get an idea of the trend, that how effective mobilities is changing with my VGS or VT, how it is changing, or TOX, how it is changing. This is something that you should take, you should understand from this given formula. Okay, so let's move forward. Okay, last question. No, there are a few more questions. Okay, okay, there are how many attendees? There are 28 attendees. I have to write it somewhere. 28 attendees, let me write it here. Yes, 29 including me, so 28. So select true false for the following statements. For a short channel model of the transistor, due to velocity saturation, the drain current is higher than expected by the long channel model for a higher drain source voltage. No, it's wrong. What velocity saturation does is it saturates the current, the IDS, even before it has reached that pinch of voltage. The pinch of voltage is that that I said that when VDS is greater than VGS minus VT, the equation it was coming like this at this point. But if it is velocity saturated device, that happens generally in short channel MOSFETs, it will saturate even before reaching this pinch of voltage. It will saturate, say, here. Okay, why this saturation happens? Scattering and other things comes into picture. If you take a device course and go into details, there are lattice scatterings and all. These are the main, there are main few reasons behind this velocity saturation. So the first statement is wrong. It is, sorry, so it's false. Okay, that velocity saturation generally drain current is lower than expected for a long channel model. Okay, so it is not higher, it should be lower for it to be true. Okay, so second point is, due to channel length modulation, the IDS VDS graph has negative slope in the saturation region. Now you can see channel length modulation, as I already mentioned, that for channel length modulation, instead of getting such kind of curve, you will get a small increase here. Okay, a small slope you will get. Instead of getting saturated value, the voltage will slightly increase with VDS. Okay, even after it has crossed, VDS has crossed VGS minus VT, the pinch of value. Okay, now why it happens, why CLM happens? You can it is a short channel effect. You can think it of such, say, in PN junction you must have read about the space charge region, right? So what happens, one of the junction in 3D model, if I get time today in 3D model, I'll talk why it happens. What happens, one of the junction is reverse biased. Okay, generally the drain is reverse biased, because in NMOS, because in drain we are applying the higher voltage. Okay, so that in that place a space charge region is formed. For long channel devices, the thickness of the space charge region is inconsequential to us, but as we are shrinking the device, that space charge region becomes comparable to the channel length of the device. Okay, so at small lengths, my L gets reduced to L minus delta L. Okay, due to the space charge region. And when you will use this lambda, the CLM parameter is another empirical model. When you use it like this and you expand it, because 1 minus delta L by L to the power minus 1, it will become, then when you expand it, you will get a term, and this delta L is dependent on VDS, right? Because if you increase the VDS, my space charge region will increase. Okay, so as we are applying higher and higher voltages, my IDS starts growing up. So this would lead to something, a lambda VDS term will come with the IDS expression. Okay, that's why I get a small increase in current. Okay, see, so given due to channel length modulation, the IDS VDS graph has negative slope in the saturation region. So simple, V equal to IR. So my it is increasing means my radius is resistance is decreasing, right? So VDS IDS curve, it will be, slope will be positive. So IDS VDS curve, the slope would be negative. Okay, so it is true. I think some of you guys have internet issues, everyone's leaving and joining again. Okay, just give me a minute. Yes, it is true. Sorry. Due to channel length modulation, graph has negative slope in the saturation region. Just negative slope. See, current is increasing, right? Current is increasing. So the slope is how much? Slope is positive. If it was not increasing, the slope would be 0. If it was decreasing, the slope would be negative. As the current is increasing, IDS VDS, the slope would be positive, right? So it will be, second one will also be false. Third one is, due to mobility degradation, the drain current is lower than expected by the long channel model for higher gate source voltage. See, it is saying mobility degradation, means my mu1 is reducing, mobility is degrading. So how much mu1 was expected? It will be less than that. If mu1 reduces, it's simple that if I put it here, if my mu1 is reducing, my IDS is obviously it will reduce, right? So the current is lower than expected. So it is true. It is true. So it is false, false, true. False, false, true. Okay. Okay. Now again, an interesting question. For a short channel model, the following are true. I have to find whether it is true or not, where Vset is the saturation velocity of electrons and Vgt is Vgs minus Vt. Fine. So VDS saturation is given as, okay, sir has directly given this formula in the lectures. If you see, the formula is VDS for saturation. Let me write it in small. VDS in saturation is equals to Vc into Vgs minus Vt, which is written as Vgt. Okay, Vgs minus Vt plus Vc. So I can rewrite it as Vc Vgt plus Vc. As here minus is given, so it is false. Okay, as it should be plus, as minus is given, so it is false. Fine. Now it has been asked whether IDS saturation is equals to this expression. What sir is given, sir has directly given it in his lectures. It is given IDS is equals to WCox into VGT square divided by Vc plus Vgt into Vset. Fine. So you can see WCox Vgt square, WCox Vgt square, Vset, Vgt plus Vset, everything is matching, so it is also it is true. It's true. Now the third expression is nothing, just I have to tweak it. Okay, so if I write these terms together, what it will be? WCox Vgt into Vset. What is left is Vgt by Vc plus Vgt. I have just broken it down into two terms. Okay, so now I know from here, if I take this Vc here, the denominator, simply I am getting this term. I am getting this term Vgt by Vc plus Vgt. So it will become WCox Vgt Vset into VDS saturation divided by Vc. Okay, VDS saturation by Vc. So it is also true. Hope it's clear, right? I hope it's clear to you. It's simple, nothing. Just you have to take it in that side and you have to take it the expression out and you have to substitute it and you will get the value. So it is false to true. False to true. Okay. Now we have got another numerical. How many questions are left? 2 questions are left. I am not able to understand the last steps, sir. Okay, sure. Let me reiterate for you. See, here I hope this much is understandable, right? That I have taken this equation and I have separated this Vgt square. One Vgt I have written here, another Vgt I have written here inside this bracket. Okay, I have taken this Vgt square, I have separated it, I have written one part here and another part I have written here Vgt by Vct plus Vgt. Now let me write it here clearly. Okay, from this expression I can find out this is equal, or VDS set by Vc. I have taken the Vc, I have taken this Vc, I have taken this Vc here. Okay, is equals to Vgs minus Vt, that is Vgt, divided by Vgs minus Vgt, that is Vgt, plus Vc. Let me call it equation A. Okay, this is equation A. So I will be substituting this by equation A. Okay, so if I substitute Vgt by Vgt plus Vc, this part, if I substitute this one, VGT by VC plus VGT, what I will get? I will get this term, VDS set, VDS saturation by VC. So I have written this term as this VDS set by VC. Hope it's understandable. Okay. Fine. Okay. Let us move on. So next question is 15 nanometer long transistor has a gate oxide thickness of 1.05 nanometer. What is the gate capacitance per micron of width? Simple, class 12 student can do it. Okay, we know what it is. Capacitance is equals to A epsilon by D, parallel plate capacitor, right? Now what is A? A is equals to W into L, width of the transistor by length of the transistor, into epsilon naught is epsilon R into epsilon naught. D is D is here T ox, because the charge is stored in the oxide region of the capacitor. If you go through details where the charges are stored, like parasitic charges and all, you will see it is almost near the oxide only. Okay, there are interface trap charges, there are other kind of charges which are introduced during fabrication. The sodium and potassium ions that are present, they gets imbibed in the oxide layer, and they can be lifetime killer for MOSFETs also. Okay, if you study the device level physics of it, you will find that most of the charges reside in the oxide or near the oxide. We can approximately take all the charges are present in the oxide. Okay, so here it is said what is the gate capacitance per micron of width. So he has asked me to find gate capacitance per micron of width, means C by W. Okay, he has asked gate capacitance per micron of width. So it would be L epsilon R epsilon naught by T ox. Simple. L is 50 nanometer. So let me write it in centimeter. Okay, so 10 to the power minus 7. So epsilon is oxide is 3.9 into 8.854 into 10 to the power minus 14 farad per centimeter divided by T ox. T ox is given as 1.05 nanometer. So 1.05 into 10 to the power minus 7. Fine. Okay, so solve it. I have done it. You will get something as, how much I got? You will get the value as 1.64 into 10 to the power minus 11 farad per centimeter you will get. Okay, now it is 10 to the power minus 11 farad, so the value is given in femtofarad per micrometer. So if I convert it, 1.64 10 to the power minus 15 if I write, I have to add 10 to the power 4. Okay, let me write it. So minus 11, let me add minus 4, 10 to the power plus 4, this is basically 1 farad per centimeter. So this and this will become minus 15, that is femto. So it will become 1.64 femto, and it is 10 to the power 4, and if I take this 10 to the power 4 below, it will become minus 10 to the power 4, and centimeter means 10 to the power minus 2, so it will become 10 to the power minus 6 meters. So it will be femto farad per micrometer. So the answer is 1.64 femtofarad per micrometer. Hope it's clear. Okay, so we are coming to the last question. We still have some time left. We have 40 minutes left. I can easily go and talk about that part, 2T and 3T MOS. Okay, so the last question is, choose the correct option regarding the statements. Okay, increasing the source body voltage has no effect on the threshold voltage. Now I don't know whether you know or not, but there is something called body effect. If you change the source and body voltage, your threshold voltage of the transistor changes. If you go to the deep device physics of it, we'll understand why it changes. But for your simplicity, I will be giving you the equation for body effect. For body effect, the transistor threshold voltage Vt is generally modified when a particular source voltage, say VSB, is applied. So my Vt0 was my initial threshold voltage. So it will change by gamma. Gamma is called the body effect coefficient. It is also an empirical parameter which is generally obtained by fitting the curves, or you can also derive it analytically. Okay, so here it will come mod of 2 of phi f plus VSB, okay, minus 2 of phi f. Okay, so what is phi f and phi s? So we have to look into the MOSFET band structures. Phi f is basically psi s, phi f. Phi f is basically the difference between uh, Fermi level and intrinsic Fermi level, EF and EI. It is called the contact potential. Okay, so here you can see the Vt is directly proportional to gamma root VSB. See this one. Someone has asked me a question. Let me check. No. Okay. So Vt is proportional to gamma root under VSB. So if I increasing and gamma, let me write the expression of gamma as well. Okay. Gamma is equals to under root 2q and a ks epsilon naught. This is basically epsilon ks epsilon naught, that is epsilon r epsilon naught, same thing, by Cox. And is the doping. So body effect coefficient also depends on doping. So if you change the doping, you can change the Vt. If you change the source body voltage, you can change the Vt. Okay, so one can take multiple approaches to change the threshold voltage of a device and thus get a different current. If you want to design it to get different Vt, in the design part you can change the VSB. In the device part, if you want to change it during fabrication, you can do it with this doping concentrations, and there are other methods also by which you can change the threshold voltage of an MOSFET. So increasing source body voltage has no effect on the threshold voltage is false. The slope of IDS VDS curve in the saturation region of a short channel transistor affected by channel length modulation is inversely proportional to the output resistance. So okay, let us understand what it is told. It is told that the IDS, sorry, my handwriting is not that good. The IDS VDS curve in the saturation region of a short channel transistor. So it is for long channel and this is for short channel. Okay, for a short channel transistor affected by CLM is inversely proportional to the output resistance. So you can understand from here, as my current is increasing, as my current is increasing with VDS, so my resistance is decreasing with VDS. Okay, so as my VDS is increasing implies IDS is increasing, so my R is decreasing. So it is true. Fine. I hope it's clear. Okay, and it is finally it is said for NMOS VGT is defined as VGS plus VT. No, sir has already defined that he has taken VGT as VGS minus VT. So it is also false. Okay, so it is false, true, false. So it is false, true, false. Fine. With this, our week 0 and week 1 sure. Yes. Just give me a minute, let me draw it for you. What you are saying, past transistor logic you are talking about? Okay, okay, like Yes. Okay. So the equation of, I think you are talking about such thing like something like this. IDS was there, then there was some constant term, then minimum was given, then VGS minus VT, or some other terms VDS, something like this was given, right? Okay, input comma VGS minus VT. Okay, so input here I think was VDS, correct? Okay, so you can also modify it with using that vset value. You can add another term, that vset, sorry, VDS set. Okay, so what is happening here? If you look carefully into this IDS versus VDS curve for long channel transistor, it is like this, right? Okay, now if my VDS is here, if the VDS is here, so my VDS I okay, if my VDS is here, what I will be doing, I will be taking and I will be replacing this equation with VDS. So let me write that equation for you. If I can recall that, I have also read that it is mu Cox W by L. What they have did, they have taken VDS as common, and they have taken VGS minus VT minus VDS by 2. Okay, now you can see for saturation region, this becomes VGS minus VT square by 2. This term becomes, okay, this term becomes, okay. So what they are doing, they are defining it in such a way that whatever you do, they are using, I think, either this one or this one, I cannot recall exactly. What they are doing, if VDS is less than my VGS minus VT, okay, if this VDS is less than VGS minus VT, what I will be doing, I will be using this expression, okay, this expression I will be using. And if my VGS minus VT is less than this VDS, that is if my VDS is somewhere here, okay, then whatever the VDS, I don't care, my expression will contain VGS minus VT term, this term, okay. Then I will be using this equation. You are getting my point? So it will become, yes, it will become something like this, right? So if my VDS, if my VDS, it is my VGS minus VT. If my VDS is, say it is my VDS 1, okay. So here which one is the minimum? This is the minimum, right? VDS 1. So I will be using the equation is written in such a manner, this equation is written in such a manner, my VDS term will be used and I will get this equation, okay. And if say this is VDS 2, here VDS 2 is greater than VGS minus VT, so this equation, when I will substitute it in this equation, the minimum as VGS minus VT, I will get this equation. Got my point? So yes, something, and if my VDS saturation was there, say my VDS saturation is the minimum, here it is the VDS set, okay, then I will replace this VDS set here in this minimum equation, and I will get something as mu Cox W by L VGS minus VT into VDS set I will get, okay, minus VDS set by 2, VDS set square by 2, I will get something like this, okay. So this is nothing, I forgot the name of this equation, but basically it's an approach where we are trying to collectively bring all the three conditions in one equation, okay. It is nothing, it is just fancy way of writing all these three equations that I have written, okay. That's why the minimum value was used, okay. Okay, fine, yeah, most welcome. So one more guy has raised his hand. Who is this? You can talk. You can ask your question. Someone has raised the hand. If you have any question, you can ask it. Okay, no one. Fine. So if you have any question at any point, you can raise your hand and you can ask question. Okay, so how much time is left? We have half an hour left. So I'll try to quickly talk about 2T MOS and 3T MOS. Okay. So one guy has asked what is the difference between this depletion and accumulation region. So I hope he is present with us as of now. Say it is a MOS capacitor. The upper layer is metal, middle layer is oxide, and the bottom layer is semiconductor. Okay, so metal oxide semiconductor. So say it is an p-type silicon. Okay, this is called the gate terminal, and this is the body terminal which I have grounded. Okay, so let us see what happens when I apply different voltages at the gate. Okay, I will be trying to see it analytically. Sorry, qualitatively. We will not go to quantitative analysis, that what will be the equation, how much charge will be stored. We will be seeing what is happening basically. Okay, say I am applying a negative volt. This is Vg. First I have given this Vg. First this Vg is negative. Okay, so when I apply a negative voltage here, as it is a p-type silicon, what it will do, it will start attracting holes near the oxide. Okay, so negative voltage will attract holes near the oxide. So this is called accumulation condition, where the surface the surface below the oxide is accumulating the majority carrier that was already present. The majority carrier in p-type silicon is holes. So it is called the accumulation condition. And if I plot here CGG by Cox, CGG is my gate voltage and Cox is the oxide voltage. If I draw the normalized curve here for accumulation region, I will get something like this. Okay, that is straight line. How much voltage you apply, it doesn't matter, because the electric field will be terminated here only. Whatever negative voltage, electric field will be terminated here, or sorry, or reverse. Okay, in the surface only, my effective oxide thickness will not change, so I will get a constant capacitance here. Now let us see what happens when we apply a small positive voltage in the gate. The gate voltage is positive, but still it's small. Okay, positive Vg. What it will do, it will start, this positive voltage will start repelling this holes. All the holes that were present will get repelled away from this oxide's interface. Okay, so as oxides are going away, this place becomes devoid, this region becomes devoid of free carriers. This region becomes depleted of majority carriers that was present here, that were holes. Okay, so as this place is becoming devoid of majority carriers, this place kind of starts behaving as a dielectric, and can be thought of that my effective Tox is increased by a little amount, not a little amount. My effective Tox can be thought that it has, from initial Tox, say it was Tox prime, or it was Tox, my Tox is increased from Tox to Tox prime due to this condition. And as I keep on doing it, my capacitance will keep on dropping. Okay, now what happens if I increase this voltage further? Okay, so it is to be noted that as this is a p-type silicon, holes are majority carriers, but electrons are still present, right? From where electrons are coming, if you ask me, they are coming from electron hole pair generation, thermal generation. From electron hole pair generation, electrons are still present in the vicinity, might be in small number, but they are still present. This electron starts moving towards this interface. Okay, And when sufficient amount of electron gathers around this region, this interface starts behaving as n-type instead of p-type. This is called inversion. That is, my original semiconductor has been inverted from p-type to n-type. So in NMOS transistor, the body is p-type. NMOS is basically, we call an NMOS where the channel that is formed, this is called a channel, okay. The channel that is formed is n-type electrons. So the body would be p-type. So NMOS body is p-type, for PMOS body is n-type, vice versa, okay. Now one more thing, initially when the effective oxide thickness is increased, my TOX prime on that time has increased, right? But now again when electrons has gathered in this position, my electric field will again terminate at the interface, restoring my T oxide value to TOX, the initial TOX. Okay, so it will go up and it will restore to its previous value. Okay, it will restore to its previous value. So it is my accumulation region, it is my depletion region, and it is my inversion region. Now, how much electrons needed to be inserted for this? Basically, when inversion happens, we call it has crossed the threshold voltage VT. Many students get, even I was having confusion in my bachelor's what it is, so I thought it is important to clear out this point in front of you. Okay, then what will happen to holes in inversion as VG is increased further? Holes will be further pushed near the body, and there may be some body current also. That body current leads to some kind of leakage and increases the power consumption of the system. Okay, so if it is floating body, it will be stored there, and if it is the body is grounded, then body effect will not come into picture, and we will get some body current also. It will increase the power slightly. Okay, so now there are many interesting phenomena that happens, something called deep depletion. Instead of going back for some small time, it keeps, if you quickly increase the VG, instead of going back, it for some time it comes in front, then with time it goes back. It is called deep depletion effect. Why it happens? Because when you apply a high voltage suddenly, the time to for these holes to repel is in the order of 10 to the power minus 11 seconds. Okay, but the generation of electrons should come from electron hole pair generation, whose order is 10 to the power minus 6 seconds. Okay, here it is reducing by 1 by root. Okay, 1 by root, like here it is falling at this rate. So from 10 to the power minus 11 to 10 to the power minus 6 second, even if you have applied higher voltage VG here, it is not able to recover because electrons are still not present here. Electrons have not been generated yet. So instead of going back, it further slides down. It is called deep depletion condition. Okay, so it is I am going to much more device level physics. Then when electron hole pair is like again it is generated at 10 to the power minus 6 second or lower, also or higher time, it will go back to this curve. And there is something called as high frequency curve where it goes in a straight manner, because the frequency, if I give high frequency instead of, if I give an high frequency in the VG, the electrons doesn't get enough time to get accumulated here, so it will go straight. So there are many interesting things that happens in the device of this MOSFET. The MOSFET that you are using is an like phenomenal device. Okay, so that what is happening inside is really interesting to study. Okay, so this is the basic of 2T MOS. So now more 15 minutes are left, 15-20 minutes. So let me go into the 3T MOS. Okay, now I will be giving you an important and interesting question to solve. I thought that I will be giving you 10 minutes to solve it, but I don't think so time will permit, so I will be solving it for you. Okay, so let us take a the two terminal MOS device that I have discussed just now and make the question a little bit more interesting. Metal oxide semiconductor was present. Now let us assume there is another n plus region present here, again oxide. Okay, okay, so there is a switch here S2, and there are two terminals here, one is VD, one is ground. Okay, and here there is another switch S1, and here are also two terminals are present. One is VG, one is ground. Okay, this is VG, and VD is greater than VG. Now let me ask an interesting question. I don't know whether you have think about it or not. Say I am having the MOSFET in saturation region, that is greater than VGS. Say the MOSFET is in on condition, okay, that is it has VGS has crossed VT. Inversion has happened, strong inversion. Can anyone tell me, there are two junctions present here? One is drain and channel junction, another is source and channel junction. Can anyone tell me which junction is in forward bias, or are the junctions both forward bias or both reverse bias, or one in forward bias, one in reverse bias? Can anyone tell me? Think for 2 minutes and try to come up with an answer. Okay, by that time let me write the question. If anyone comes up with answer, you can raise your hand. Okay, so the condition is, question is, at t equals to 0, my switch 1, the switch 1, this switch 1, this switch, okay, switch 1 is given VG, that is this VG. Switch 1 is thrown from ground to VG. Okay, what will be the capacitance versus voltage curve at t equals to 0 plus and t equals to t not equals to t tends to infinity? It will come from this curve. I am asking to plot you this curve, but in these three different conditions. Sir, can you please share the slides to us? Okay, basically I will be uploading this whole video to the YouTube, so you can go and you can make your own notes from YouTube channel. Okay, it will be shared with you. It is requirement of NPTEL to share upload these videos in the YouTube, so you can directly go collect it from there. If I share it with you, then you will not try make your own notes, so it is better you make your own notes. Okay, so go, if you need you can recap it and you can make the notes. So anyone, any thoughts on it? Any thoughts, anyone? You can no one will judge you here, right? So if anyone is coming up, why you were saying that? Any reason for you to say this? See, drain is given high voltage, right? VD is given high voltage, if you can recall. And if VD is what? VD is N plus type, right? So if VD is high voltage is given to N side, remember PN junction, whether it is forward biased or reverse biased, it is reverse biased. Okay, so let us see what happens. Let me first answer this question. When S2 is open, okay, when S2 is open, it is nothing but a two-terminal MOS structure. When my S2 will be open, it will be simply a two-terminal MOS. It is inconsequential. This one becomes inconsequential, this N plus region. Okay, so my CGG versus COX versus VGS will be same as a two-terminal MOS structure. Okay, this is deep depletion condition. So this would be at T0 plus when switch is thrown off, because it will go to deep depletion, and at T tends to infinity it will come back to, it is also called the low frequency curve, this one. Okay, it will come back to low frequency curve. It is the B1, it is the easiest one. You should have come up with at least this one, right? It was easy. So now let me go to condition number A. What is condition number A? when S2 is grounded. S2 is grounded. Okay, see what happens. So when VGS is negative, when VGS is negative, I am applying negative voltage here, and this is grounded. So whether it is forward bias or reverse bias, can anyone say? It is grounded. My P is negative, N is grounded, so it is reverse biased. Okay, so it will not change. It will not change. But if I give this VG, say it is connected here. Now if VG is positive, that is the accumulation condition, whether it is forward biased or reverse biased. Now when VG is positive, the surface potential that will come here, psi s, is positive. So this junction becomes forward bias. Okay, so what will be my curve? Any guesses? This will be same as this one, but you will not get the deep depletion condition. This condition you will not get. Okay, it will reduce and it will again increase. It will reduce and it will again increase, but this deep depletion condition I will not get. Why? Deep depletion happens because I was not having electron hole pair generated electrons to form the channel, the inversion channel. But as it is forward biased now, the electrons can simply come in from here, from this N plus region. The electrons can simply come from N plus region, right? So my channel will be formed even at the earliest moment, at 10 to the power minus 11 second, minus 12 second, the channel will still be formed. So I will not get this deep depletion curve. Okay, this curve I will not get. So it will be simply this one. And what happens for condition number C, that is S2 is connected to VD1, where not VD1, VD, where VD is greater than VG. Now it is connected here. Okay, what will happen? It is, I am giving higher voltage to N plus. So my N plus P junction would be reverse biased. So what happens in a reverse bias condition? What happens in a reverse bias condition? See what happens. Now negative will stay as negative, it will not change. The depletion accumulation region will not change. Depletion region will not change. What about inversion region? Think what will happen. Can anyone take any guesses what will happen? See, it is reverse biased now. Okay, so any electron that is trying to trying to form the channel here, okay, any electron trying to form the channel here, remember PN junction, your PN junction lectures from your first year. What happens in a PN junction in reverse biased? What happens to the electric field? The electric field becomes very high, right? And that's why in the space charge region, the space charge region increases in the reverse biased and electric field becomes very high. And sometimes even breakdown can happen, avalanche breakdown or Zener breakdown. Why it was happening? Because electric field is high in reverse bias. So this electric field, what it will do? It will sweep the electrons. It will sweep the electrons and will not allow the channel to be formed here. Okay, or it will try to compete. The electron hole pair generation will try to bring that electrons here, and this reverse bias will try to sweep the electrons away from this channel. So I will not get this curve. I will not get it. What I will get is this, because my channel is not formed here. Channel is not formed here because the electrons are already swept by the VDS. Okay. Okay, so my channel is already, the channel cannot be formed here. Even if the channel is formed, it is formed partially. Channel cannot be formed here. So it is the condition of reverse biased. It is the condition of forward biased. Now, why I was talking about this? Why I am talking about this? These two conditions. Now let me just make one change. Let me add another N plus here. Okay. I will be just making one change here. it was your 3T structure and N plus was present. Uh, it was your metal oxide semiconductor. Okay. Now let me add one N plus and provide a high voltage here, the case number C, and let me ground it here, case number B. So I am getting two junctions here. So which case does it resemble to? This is resembling to this case, forward bias case, this case, forward bias case, grounded case. And which here I am applying a high voltage VD, this is given VG, say some voltage VG, okay, and which this one, which it is resembling to what, which condition, condition number C, right, that is reverse bias case. So this is in reverse biased and this is in forward bias. That's why if you see the charge profile, okay, the charge profile is something like this, the electron charge profile is something like this, something like this. It is tapering towards the drain side, and electric field is also high towards the drain side. That's why this velocity saturation happens near the drain side only. Okay, that's why sometimes halodopants and some things like there are some effects. It is called Dibble effect, drain induced barrier lowering. Okay, to remove them, some doping is done. These dopings are done in front of the drain. They are done both in front of drain and source because it is a symmetric device, MOSFET. I can use any terminal as drain, but this is the reason I have to make some dopings here if I want to control the short channel effects. And this is the region, as it is a reverse bias, it is trying to sweep the electrons from here. That's why the channel tapers out near the drain. And when the VDS is high enough, my channel becomes something like this. It becomes zero. It becomes zero near the drain channel junction. That's where you get the pinch off condition. That this is the point. This is A. This is this point where you are getting this pinch off condition. If you further increase VDS, it will not affect it because my channel has already at this point the electron density is already zero. All the electrons that are coming is already swept. If you further increase VDS, what will happen? It will become something like this. All the electrons that will come, they will directly go and they will not be able to form the channel here. Okay, so more 5 minutes are left. So this is your MOSFET. This is how I can start. I can start from a two-terminal MOS cap. I have shown you what happens when I apply different voltages to drain and source, and at first, last I have shown you how a MOSFET works. Okay, I hope it has cleared your it has cleared all the, if any doubts you have. I hope it should clear, this video should clear it, and I hope you have enjoyed this session. I hope it was not boring. I tried it not to make boring. Okay, so I hope you have not felt bored during this whole time. So I am ready to take feedback for today's classes so that I can incorporate some changes in the from next class onwards. So if you have any confusion or if you have any feedback for me, you can throw it towards me. I am ready to face them. So anyone, anything? Then either you have not understood anything or you have understood everything. I don't know. Okay, everyone, do one thing. Kindly write your names in this comment section. I have to copy your names. Okay. So if anyone has any question, you can ask it. Okay. So we have more 5 minutes. You have to sit for more 5 minutes. At least I have to sit. You see, I have not uploaded the video yet. The video is still being recorded. Once I have recorded this video, I will be uploading it to my YouTube channel, and via mail it will be shared with you, the link of my YouTube channel. Okay, sure, you will get a mail. Sure. And how was the class? Was it boring enough? Not enough. Was it boring or was it good? Okay. Okay, thank you for your kind comments. So everyone has written their names, right? No, everyone has not written. Okay, I'll try to go much more slower than that. Yes, I have an habit of running through the topics and talking much more faster. Actually, I thought about giving this 2T and 3T 1 hour time, but only half an hour was left, so I have to run through it. Okay, and it is more of a device level understanding, not the circuit level understanding. So I think to understand the circuit level, you should have basic knowledge how the device works. That's why I discussed this with you, and this will help you to think why these short channel effects are happening, how they are happening. So I could have added some more points that how this region is where you get this CLM effect. This is the space charge region that becomes. So if that time permits, I will take it up in another class, and I will try to introduce some small discussion topics like this in every lecture, so that you enjoyed it, and it clears your concept also. And sometimes I will make some small questions for you, and if time permits, I will give you, and you will enjoy solving them. I hope so. Should I share my IITK website or Gmail? Let me share my Gmail website because it is what is registered in NPTEL. Huh? Okay, I've shared my email ID with you. So more 1 minute left. 1 minute or 2 minute? 1 minute. Okay, guys. Thank you. If you want, you can leave. If you have no further questions, thank you for joining. Hope you guys have enjoyed it. Sure. Like I will be having the session every Friday from 6 to 8. This is the slot that has been booked for me. So we'll be having same time next every week up to next 11 weeks. Okay, thank you. Okay, you guys, you can leave the meeting now. Let me end it. Thank you for joining.